Thanks a lot for the presentation and for organizing this beautiful workshop. This talk is based essentially with this paper made with Chiara Animali and Giovanni Marossi, and we work in formulation of the adiabatic renormalization with a near cutoff. The outline of the talk is the following. I introduce essentially the adiabatic renormalization and the need of renormalization in curved spacetimes. Then I explain with a particular example the motivation for our work, and then how to fix the univocally the scheme of the renormalization scheme with physical prescription. So what happens in curved spacetimes is essentially the same that happened in flat spacetimes. When one try to evaluate the product of quantum operator, the expectation value of quantum operator in the same point, one usually obtain some divergences in the DPV. And what essentially we do in flat spacetime is to subtract from the quantum expectation value the expectation value in the vacua of the Minkowski spacetimes, where the vacua is well defined from the symmetry of the system. And so now, one of the particular cases, most important, I think, case is the study of the expectation value of the energy tensor that in context of gravity, of course, is so important because we enter directly in the Einstein equation. And if we try to renormalize this quantity in curved spacetime, subtracting the expectation value in the Minkowski vacua, we obtain new divergences. A quantity that again divergence in the UV, essentially for the presence of the interaction with gravity. One of the most important problems in the context of gravity is essentially the choice of this vacua. Indeed, there is not a preferred choice of the vacua because we have also no preferred choice for the coordinate system in the same way. Indeed, if we try to define in the standard way the vacua as the minimal energy vacua, defined in this way by some quantum field and its annihilation operator. So this state here is the state that contains zero free particles, if we want. Then in the time evolution, due to the presence of a non-trivial background, in this case the gravity, there is the so-called mixed modes between positive and negative frequency modes. So at some time t larger than t0, we obtain a field that is evolved, that can be written in this way, where the new mode function g and the creation annihilation operator b are related by the so-called Bokolivo transformation with the previous ones. And if we try to evaluate the vacua, the starting vacua, we obtain actually that there is a field by an n number of phi particles. So in order to fix to choose a particular vacua, we can require some physical prescription. Essentially, a good vacua should be such that if we consider an state with namely a particle with an energy larger than the energy of the system. In the case of cosmology, for example, the energy is given by the curvature. Then such a state cannot be excited. So in particular, if the change in time of the energy of the system of the curvature in the case of cosmology is adiabatic, then the number of particles of some mode k should be a constant. Thus, we define the adiabatic vacua as the vacua that minimize the particle creation due to the presence of the time-dependent metric. And in this way, we can define the adiabatic renormalization prescription as the subtraction of the modes evaluated in the adiabatic vacuum. In this context, the mode function are given by the W kappa B ansatz, and we can define the adiabatic mode function up to an order n that should match the energy dimension of the operator that we want to renormalize, and then subtract the adiabatic term from the bare quantities. For example, in the case of the energy tensor, we subtract the adiabatic counterpart calculated at the order 4, because the energy tensor has a dimension in energy 4, and this is the renormalized quantity. So let's try to understand better how to work with the adiabatic normalization and why we introduce an here cutoff. We consider this particular model where an pseudo-scalar inflaton field that gives us the background, the homogeneous background, is coupled to an one gauge field in this way, with this coupling, a sort of Chern-Simons coupling. Essentially, due to the interaction with the ground field phi, the quantum fluctuation of the gauge field are amplified, and then they back reacts in the background, essentially in the equation of the equation of motion of the inflaton fields and the Friedman equation. So we are interested in the calculation of essentially these two quantities: the energy density that enter in the Friedman equation, and the helicity integral that enter in the equation of motion of the inflaton fields. Thus, we consider in particular the Sitter background, and in this context, the mode function where we chose the circular polarization, plus and minus, can be solved analytically in terms of the so-called Wien-Tucker function that depends on this constant parameter C that essentially is related to the with the coupling with the inflaton fields. So inserting in the previous integral, one is able to calculate analytically this integral, and inserting an UV cutoff in order to see better the UV divergences, one obtain this expression here for the energy density and for the helicity integral, where in the helicity integral we can see that there is a quadratic and logarithmic divergences in the UV, and quadratic and logarithmic divergence in the case of the helicity integral, and in the other hand are well defined in the ER, as we expect from here. So essentially, we now want to subtract this divergence in order to obtain a renormalized quantity, and we apply the adiabatic subtraction. So as I said before, we have to calculate our adiabatic counterpart and subtract them to the previous bare quantities. Now, in order to obtain the adiabatic counterpart, we firstly make a W kappa B approximation ansatz for the mode function in this way here. Then putting into the equation of motion, where we insert also an mass regulator M that should be sent to 0 at the end of our calculation, we are able to obtain this exact expression for the W kappa B frequency that is non-linear, and so generally cannot be solved, at least in some approximation, the adiabatic approximation. So essentially, we ask that we demand that the frequencies are slowly changing the function in time, and inserting this parameter epsilon that take into account the number of time derivatives or curvature derivatives, if you want, we can express this function here as a power series in epsilon. And iteratively, we can obtain order by order this solution. For this case, as I said before, we need at least the 4 order for this expression. Then the standard adiabatic regularization can be expressed in this way. We integrate the expression before into here the A plus minus. We put the adiabatic expression up to the 4 order and integrate from 0 to the same UV cutoff. Now, as shown by Ballardini and Hall, one is able in this way to match exactly the UV divergences, and on the other hand, one obtain this dependence from the logarithm of the mass regulator M that should be sent to 0. So there is this the price of a new divergence in the year that is unphysical, is generated only from the renormalization procedure. We can ask ourselves why there is this new problem, if you want. Essentially, in one hand, we know that the adiabatic normalization is related to the need of subtract UV divergences. It's founded on the adiabatic vacua of, if you want, in the adiabatic ansatz that match exactly the mode function in the DQV, where essentially the space is like Minkowski 1. And the adiabatic vacua or the WKB approximation is well defined only if the modes fill small curvature, or actually is the frequency that evolve slowly in time. In translating in a cosmological word, we can say this point here, saying that the WKB ansatz is a good approximation for the mode function only for modes that are inside the horizon, so are sub-horizon. So we suggest that actually the adiabatic subtraction should be considered only up to an ER cutoff that should be related to the scale where the WKB approximation is no more a good approximation. That is the scale in the case of comoving given by the Hubble curvature. And in this way, we introduce a new parameter beta, that is this coefficient here, that should be fixed at the end of the calculation by some physical prescription in full agreement with all the renormalization scheme also in flat spacetimes, for example. So let's try to see what happened. We can evaluate our new adiabatic term if you want, integrating the adiabatic mode function up from the ER cutoff introduced before up to the UV cutoff, and one obtain, of course, the matching in the UV divergences as before. And now, in the other hand, the limits of the mass regulation to 0 is well defined. There is no presence here, but there is the presence of the our new parameter beta.
You got
now
one more minute, Pietro.
Yeah, okay, I can conclude the rapid. Then we have to fix univocally this parameter, and now if we consider a conformally filled with gravity, is a general feature that in the classical level, the trace of this that of the energy tensor of this field is 0, indeed conformal coupling. But when one introduces the quantum correction, so the renormalization procedure, so on, one obtain actually that the trace is no more 0, is related to the trace of the regulator term, and this is called the conformal anomaly. that should be obtained in all good renormalization methods. Now, looking at our mode function, we see that in the limit where the mass is given to is sent to 0, and the coupling with the field is sent to 0, actually the two helicities are equivalent to two conformal mass scalar fields. In looking at the final expression of the Timoneau and taking the energy density, we see that in this limit, the only term that survives is this one. And then requiring the matching with the, this should be twice the energy density of the two mass scalar fields. And then requiring this matching, we're able to fix univocally the parameter beta. Then we are able to obtain the physical finite results for the two quantities, energy density and helicity integral. And then this is a univocally fixed prescription that give us, of course, the conformal anomaly in the proper limit, because we study it in this way, and give also an finite result for this quantity that should be used in the computation feedback reaction of the system. So in the next, we want to study the phenomenological implications of such quantities in our system, and also apply to other systems that are the same peculiarity, if you want, as for example the case of pseudo-scalar field coupled with Chern-Simon gravitational term. And okay, these are my conclusions. Thanks for.
Thank you, Pietro, for such a nice talk. We have time for one or perhaps two questions. So please, if anyone has a question, raise your hand or simply unmute yourself and ask. Okay, Antonio Ferreiro has one question. Antonio, please go on.
Thank you, Pedro, for your talk. It was very interesting. So I have many questions. I will only ask one, and maybe I write you on Slack the other.
Okay. Okay.
It's a long list, not so long, but well, my question is that the regularization program you have established with this infrared cutoff, adiabatic regularization is usually controversial because it's non-covariant when you express it as a mode integral, and you are usually you have to prove that it is covariant. And for example, one method is just to take the stress energy tensor, use dimensional regularization, for example, and to see if it is covariant, if you can express it as in a covariant way, and also if it can then be renormalized into the coupling constants of your theory. So I would like to ask if you have checked that with your method, since it is a typical result that when you introduce cutoffs in your integrals, you get non-covariant results. So I don't know if you have checked that.
Yes. No, actually, we don't check this thing, essentially because our point should be that okay, the UV cutoff that we introduce here is only inserted just for give us the this cutoff here, for give us the power of divergence in the UV. But essentially, in the prescription of adiabatic normalization, one have to subtract directly in mode by mode the terms, and so actually this UV cutoff is not present in the calculation. In the other hand, the other cutoff, the ER cutoff, is only a way to say that essentially the adiabatic counter term go to 0 rapidly when the modes ask from the horizon in a cosmological term. Okay. The only thing that we have shown in our paper is that related to the conservation of the energy tensor is that actually this cutoff here don't give any problem in the conservation, essentially because the the only effect that one can expect from this object here is that you change the time derivative in the energy density conservation, but actually it doesn't happen because essentially this is a comoving cutoff, and actually it's not time dependent. Okay, so essentially this is only the only one check that we made. Thanks for your question.
Okay, thank you.
We can discuss better in the Slack, I think.
Yeah, well, thank you.
Okay, so I encourage if there are any more questions to put them on the Slack channel. And we thank again Pietro for this wonderful talk. Thank you very much.